Okay, we just finished discussing about the convolutional layers. So like I said before during the previous lecture, the convolutional layers is not just involved with only the convolutional operation. Doesn't matter is it a two-dimensional convolutional operation or one-dimensional convolution operation or three-dimensional convolution operation. It also include with activation functions. Okay, in the meantime, just remember that meanings that in convolutional layers, it's not only involve a convolutional operation, it's also involved with activation functions. So instead of convolutional layer in CNN, you also need to we need also to discuss about the other main item involved in CNN. Okay, such as there's a 4 components there. Actually it's not 4 component, it should be 5. Okay, the last one is what we call as a batch normalization. Okay, among these 5 items, some of it is also involved in convolutional layer, meaning that previously I just said that convolutional layer is consists of 2 operation. One is a convolutional operation, another one is activation function. So that's why in order for you to produce feature maps or activation maps, or in other words is a matrix of O, then you need to apply the convolution. After that, once you get the matrix of nets, then you need to apply the activation function to produce the O matrix, which is also known as activation maps or feature maps. Okay, some book call it activation maps, and if you refer to other books, it's called as feature maps. Okay, so among this item, you will see that stride is also happen at the convolutional layer. Padding is also happen at the convolution layer, but that does not mean it's only happen in this convolution layer, it also happen to the other layers as well. Okay, meaning that stride can be happen at the convolutional layer, stride and padding can be happen either at the convolution layer or with other layers. And then we will discuss about the polling operation. Okay, this is another layers. Okay, instead of convolutional layer, then you also have what we call a pooling operation, or you can also set pooling layer is referred to pooling operation is referred to pooling layer. Okay, and then of course activation function is the only happen, is the thing, the process which is only happen at the convolutional layer, where actually this is where I discussed before, is that if you need to have a activation function to produce the matrix of your O. Okay, so which is also known as either feature maps, feature or activation maps. And then batch normalization. Batch normalization is something that will happen at convolutional layer as well. Okay, but not for other layers. Okay, let's go back to the example of CNN. We go back to the slide that consists of example of CNN. So then we will a little bit understand what I'm talking about here. Okay, this one. Okay, this is the example of CNN architectures. As you can see that, okay, this is where the convolutional layer is located in this structure. Okay, this is your convolutional layer, and then same as this one. Okay, because it's a convolution, so this is where you will have another convolutional layer. So as you can see that in order to obtain this feature map, then inside this convolutional layer you need to have an activation function, because the feature map is referred to your O. Okay, this is also same. This is your O of and this is yeah, this is your O. And then instead of, you can see that from here you can see that there's a basic component. There is a few component you need to know in order for you to develop CNN. Okay, one is a convolutional layer, another one is subsampling over here. Okay, this is also known as what we call as pooling layer. Okay, pooling layer that is referred to this item number 3, pooling operation. Okay, pooling operation or pooling layer is also known as a subsampling in this diagram. Okay, and then you can see that you will have one layer is called convolutional layer. You produce this one, and then this feature map will go into pooling layer, and then from the pooling layer it will shrink the feature map. The existing feature map will be shrink into small sizes, and then once you have these small sizes of feature map, you apply a convolutional layer to this input, then you produce another feature map, which is another O. This is other O, this is another O, because this O is different from this O. As you can see that this O is produced by this convolutional, while this O is produced by this convolutional layer. And then you have another subsampling. This is where you will apply again the pooling layers. Okay, this is where actually another pooling layer exists. And finally, okay, this is happen for any CN architecture, because the shape should be shrink from the big size 2-dimensional or 3-dimensional matrix is going towards shrink the size up until 1-dimensional matrix before you can produce one output here, which is will be represent the label of this image. Okay, so normally for CNN it will end up with what we call as a fully connected layers. Okay, if you okay, fully connected layers. If you remember what is fully connected layers, like I discussed in the during the first introduction of this chapter, fully connected layer is related to matrix multiplication. So what is the meaning by matrix multiplication? Is actually is the similar process that you have done in your artificial neural network, because artificial neural network what happen at the artificial neural network is that each and every layer you apply the fully connected layer. Even we don't call it as a fully connected layer, because at that time we don't have the name for that, because we don't start learning about deep learning. We don't learn deep learning in the previous chapter. So once we learn the deep learning, actually that operation in deep learning try to differentiate between convolutional layer and fully connected layer. So that's why there's a name for that. Actually, when you have a network which is fully connected like that, okay, you have a network which has a fully connected like that, so it's called a fully connected layer, where actually that is where the matrix multiplication happens. So in other words, what is actually CNN is about is not just you can see that in CNN we have a lot of operation. It's not just matrix multiplication, while in shallow neural network or deep neural network or artificial neural network that you learned before, we only have one operation, which is called matrix multiplication. And in this chapter, it is also known as a fully connected layer. So in CNN, one of the, in my opinion, why they call it CNN, because most of the layers involved in this architecture is a convolutional layer. So that's why, since the convolutional operation is dominant inside this architecture, that's why they call it a convolutional neural network. Even you can see, you realize that in CNN it's not just involved with convolutional layer, you can also see there's a pooling layer as well as a fully connected layers. So this is how, in general, this is what happened. Sometimes you have multiple convolutional layer, means that from start up until end you can have several convolution layer, and then you also consist of, it's not just a convolution layer, it also involve a pooling layers there. The purpose of pooling layers there is to shrink the size, because in general CNN architecture should be shrink from this left hand side to the right hand side. The matrix, the size of matrix or feature map should be shrinks towards at the end you will find out there's a one-dimensional matrix only. So and because at the end you need only to produce only one output, which is represent the level of this image. So that's why that the architecture is like a shrinking there. So one way to shrink the size of the matrix, they are using a subsampling, which is referred to pooling layer, because pooling layer is the only way you can reduce the size, and then before you end up with a fully connected layer. This is also normal to CNN. You will end up with a fully connected layers before you decide what actually this image is referred to. Is it a robot, or in other example, is it a cat or dog or something? So that is how it's work. So back to this discussion over here. So you can see that in general, CNN actually you have how many components? You have a convolutional layer, and then you also have a pooling layer, and then the other one is a fully connected layers. Okay, and then pooling here is divided into two. Later we'll discuss about that. Okay, by having these three is enough for you to build your own CNN architecture. Actually, there's another operation that I don't cover in your syllabus, is known as dropout. Okay, dropout layer. Actually, dropout, and the purpose of dropout is similar to, we can consider as similar to pooling layers. Okay, so later you will realize that maybe if you have some time to explore CNN, you will find out that most of the time when people design the CNN architectures, if they design the CNN architecture, you will find out that some people use this convolutional layer plus dropout. Okay, I just put it dropout layer plus fully connected layer, and some people try to design it using convolutional layer plus pooling layer plus fully connected layer, because both layer actually the purpose are almost similar, which is a subsampling, meaning that the purpose is you want to shrink the size. So instead of using a pooling layer, you can also use a dropout layer to do that. But in your course, we just focus on only in pooling layer. Okay, we will not discuss the dropout layer, because by having convolutional layer, pooling layer as well as fully connected layer is enough for you to build the CNN model or CNN architectures. Okay, so let's start with the stride. Okay, number one, which is stride. So what is stride? Stride is just the step size. Okay, remember when you are, if you are talking about the convolutional operation, you are sliding the window. You should remember that this, let's say this is your image, and then that is your filter. You are sliding the filter to the entire image. Okay, that is what you do in order for you to apply the convolutional operation of this image up until this here. So stride is refer to the step size. If you, let's say you set your stride during the convolution operation, you want to select your stride equal to 1. So meaning that for each and every pixel, the sliding window will jump only one step. Okay, so like what we have done in this slide. Yep, this one. Okay, this one, the stride is equal to 1, because you can see that, let me delete this white markers there. So you can see that the transition there. If you want to find the S7, you slide this window into this area of image, and then if you want to find the net, let's consider this as a O8 here. Okay, then you need to step just one pixels from here to here. Okay, meaning that from here to here is just 1 pixel. So this is the meaning when you set your convolutional operation with stride equal to 1. But you can also adjust it into any number which is not only 1 or is more than 1. For example, let's say you set your stride equal to 2. So that's mean the first window is start here. Okay, the first convolutional will start here, and then the second convolutional operation, instead of just sliding 1 step only, it will jump 2 steps, meaning that the second convolution operation, it will start here. Okay, that is the meaning where that is what is meaning by when stride is set into 2. Okay, so means that instead of you are jump 1 step, you jump 2 step. Okay, sorry, I let me undo this one. Oh, we cannot undo because I draw it wrongly, because it should be here. Okay, the window should be here. Sorry. Yep, because from here, then you step, you move 2 steps ahead to this part. That is the meaning by stride. So now you are do the convolution between this and this window for the second convolutional operation. For this one, if you set the stride equal to 2, of course, if you're talking about the matrix 4 times 4, is not applicable for that. You just assume this image is very big. Okay, meaning that it's not just 4 times 4, it's more than that. So if you talk about, if you set the stride equal to 2 for convolutional layer, then the convolutional operation will make the sliding filter or sliding window jump in 2 steps ahead as compared to 1 step ahead in order for it to slide from the upper left corner into lower right corner. So that is the stride size. Okay, so that's why that is the meaning by stride. Okay, so why they use the stride, why they in general, of course, for those who take the image processing, we don't have this one, because by default we always mention, or we always assume that our stride is equal to 1. But in this class, in CNN, you can change the stride number. It's not just 1, you can have 2, you can have 3, and so on. So why we need to increase more than 1 stride is actually this will make automatically your convolutional also can make some sort like a subsampling operations. inside the convolution layer. So as you can see that, remember that when I discuss this thing, okay, because again at the end CNN, in CNN you need to reduce the matrix from the bigger size into the small one. So one way to do is, again, like I discussed before, you can apply the subsampling operation, which is also known as a pooling layer, because pooling layer is a specific, the main purpose is to reduce the size of the matrix. But instead of using a pooling layer, inside the convolutional layer you can also reduce the size by having the stride which is equal to more than one. Because by having that, you will realize that, like in this example, if you jump more than one, okay, like this other one, like this example, if you jump more than one, let's say I want to find here, okay, again this is, assume this is your 07, so to get my 08 over here, we say actually when I set my stride equal to 2, then to find 08 I need to convolve my filter over here with this area, because my stride now is equal to 2. So meaning that this is the center of the region, and this is where actually when you want to find the 08, because now you are jumping from here, okay, this is the first convolutional happen. One is slide to another region is step 2 time from here to here. Okay, this is the first convolutional, and then this is the second convolutional operation, where actually the center is R9, because you are jump with 2 step ahead, because you set your stride equal to 2. So at the end, when you want to at the end, your activation map will reduce the size. Okay, it's not similar to the size. For this case, you can see that the size should be, if you stride equal to 1, then the size is shrink into 2 times 2. But if you set the stride more than 2, then imagine that you can have more and more activation map where the size is shrinking more as compared to the input image. So that is the one way to shrink the matrix. Okay, instead of you are depending on pooling layers, you can also do that. Okay, so the other component, which is, okay, that is what we call as a stride. So this is some example how you do as before. You can see that I think this is the previous example that we discussed before. Okay, this one, you can see that, let's say you set the stride equal to 1. So this is what happened to the sliding window. Let's assume this is your image 7 times 7, and then you have a filter. Then of course we just ignore the depth. Okay, doesn't matter, the depth is equal to 3 for the input image, then the filter will follow the depth size. So that's why we don't have to worry about the depth size there. What we want to emphasize more on the size of your X and Y, because the depth should be similar. Doesn't matter your input size. If the depth is equal to 3, then the filter also must follow the depth is equal to 3. So that's why we just ignore the depths there. So if you apply the convolutional filter 3 times 3 to this 7 times 7 input image, you will and you set the stride equal to 1. This is what happened. It's like okay, so it's like what we have discussed before. That is when the stride is equal to 1. So at the end, the feature maps or the activation map is equal to 5 times 5. Okay, because we start here, then our stride is equal to 1. Then you will compute here, and then at the end you will have how many matrix there at the output side, or what is the size of the activation maps produced from this convolutional. Of course, is a 5 times 5. Okay, that is if you set your stride equal to 1. So what happened if you set the stride equal to 2 for this convolutional operation? So again, it will jump. You will apply the convolutional at this point, and then because you are jumping 2 steps ahead, then you will apply at this one, and you apply at this one. So if you continue to do this, okay, it's not just a step jump towards or jump ahead at this direction, which is X. You also jump 2 steps ahead at this Y direction as well. Okay, if you set the stride equal to 2, so that's why you jump from here to here, and then you jump from here to here, and then from here to here you jump to step. Then you will have another one here, another one here, another one here, another one here, and another one. So at the end, what is the output of your activation map? It should be, of course, 3 times 3. Okay, it's just 3 times 3. Again, this is your activation map or your O matrix. Okay, because you only compute this point, at this point, this point, this point, at this point, this point, this point, and up until this point. So that's why you will only have 3 times 3 matrix if you set the stride equal to 2. So you can imagine that what is the purpose of stride. You can see that if you increase the stride more than 1, then you are not just applying the convolutional operation, you also apply something like subsampling or something like pooling layers. Okay, normally the one that make the matrix keep shrinking is a pooling layers, but in convolutional operation also you can do that, means that by having the stride size more than 2, so you keep shrinking the matrix towards to the end of your CNN architectures. Okay, so the output is 3 times 3 for stride equal to 2. So how about if we set or we apply the stride equal to 3? Can you do that? Of course, it cannot do that. Why? Because 3 times 3 is not fixed with the 7 times 7, because this is the first convolutional, and then you step 3 step ahead, 1 2 3. Okay, is good, but here it's not good because the next point you want to compute is out of bound or out of the border of this input image. So that's why for 7 times 7 input, the stride you cannot set the stride equal to 3. So of course that is also the tips behind it, that if you want to apply the stride, if you want to choose the suitable stride to be used for your input, please make sure that you also consider the size of the input image. Otherwise, if the size does not fit with the stride size that you apply, then it's not working properly. Okay, the stride size must fit with the input image or input activation maps. Okay, so at the end, this is how the formulas look like. So meaning that in general, this is how you want to this is how you want to estimate the output size based on the formula. This is your input image. Let's say this is n here is represent the size of your x and y of your input image. Okay, or the input. I don't want you to call it as a input image, otherwise you might get confused. Okay, this does not mean is only applicable for input image, but also it's also applicable for activation map. So don't get confused with that. So that's why I don't call this metric as the input image. I just call it as the input of your convolutional layers. Okay, why? Because input does not mean is only refer to input image. It can also refer to activation map. If you remember, okay, just remember these architectures. Yep, this one. Okay, this convolutional layer, the input for this convolutional layer is input image, but the input for this convolutional layer is not input image, is an activation map of the previous layer. So that's why I cannot call any input of convolutional layer as an input image, because the one that have the input image which is similar to, I mean, the one that have the input which is similar to the input image is only this layer. But this convolutional layer is apply the input is activation map of the previous layer, and the output as well is a activation map or feature maps. So that's why I cannot call this one, it's not suitable to be called this one as an input image, is a input for this convolutional operation or convolutional layer. So that's why it's better for you to call this thing, okay, this thing as your inputs only, input matrix, or that is more good than you call it as a input image, okay, because input image only happen in the first convolutional layer, but the second or the third or more the middle convolutional layer, the input is not input image anymore, it's a activation map of the previous layer. So that's why it's better for you to call this as input only. Okay, so this is the formula. As you can see that if the size is n, and then f over here is your, if your filter size, okay, this is filter size, this is your input size, okay. Normally it should be similar, it should be the x size and y size should be similar. In the previous example is 7 times 7, so that's why the n is equal to 7, and this is your filter size, 3 times 3. So if your filters, if your input size, input image, if your input matrix is 7 times 7, the filter size is 3 times 3, then in order for you to estimate the stride which is which is fit with your operational, then you need to apply this formula, because if you must get integers number, okay, it's an integer. If you get integer, then you can apply that stride. So that's why when the stride equal to 1 is okay, okay, because you will get 5 there, meaning that a 5 times 5 output or 5 times 5 activation map. If you apply stride equal to 2, then you get 3 times 3 output or 3 times 3 activation map. But if you apply stride equal to 3, then you get a floating number. So once you get a floating number, meaning that it's not fit for that operation. So that is the formula that you can apply for that.